Welcome to the India Energy Week as we assemble here to hear our panelists speak about maintenance as well as process optimization. Today we are at the juncture where most of the process industries are operating at the highest capacity. So any anomaly between in the process or the asset health has a cascading impact on the entire value chain. So here at this juncture, there are a lot of investments happening to take care of those predictions through the use of AI and the associated infrastructure. So, since this is a large topic, how we're going to spread it across is in this entire value chain, we're going to talk some things about the sensors, where it is essential to actually capture those anomalies which are coming at the field level, the compute that is required to store it, the models that are required to process this information and generate insights so that proactive actions can be taken and the execution can ensure that the asset health is restored to the best of their ability. Now, with this background, I'm happy to introduce our first speaker for the day, Mr. Anand Mayank. He comes from a technology and a strategy background. He's been associated with Power Grid, and today he's here to present how the overall transmission network could be optimized accordingly, and he's going to take this opportunity to present the framework associated with it. His overall experience in the space of transmission spans close to about 17 to 18 years, and invite Mr. Anand, please take over and start your session as well.
Hola, ¿cómo estás? ¿Estás disfrutando de IEW y Goa? Espero que tengas estancia agradable aquí. Hoy es un día hermoso. Surprised? Wondering, what is this? Actually, I was speaking English in speaking a Spanish and English conference, which is highly impactable but very low probability, which we call in transmission is HILP, high impact, low probability events. So thank you, Karthik, for introducing me and setting the precipice. I want to emphasize that earlier we have three basic needs: roti, kapda, or makan. Now we have fourth one, which is electricity. These four pillars drive our life nowadays. So why electricity is necessary? Because it can be transported easily and it is very cheap to transport it. That's what my company PowerGrid does. In next few 10 to 12 minutes, we will see what framework I am proposing to make it handle these HILP events, what if scenarios. We are working on optimization. We are using digital twins. We are using PIN networks. But what happens if there is a grid failure? Like last year you have seen in Spain and Portugal, and 2015 India has witnessed it in eastern region and northern regions. If there is a grid failure, we are on total collapse. Billions and dollars are lost due to electricity failure. So without much ado, I will start. Just introduction. It's working. I think there is some problem. Okay, finally. So you all know we have a target of 500 gigawatts non-fossil fuel by 2030. Most of it is coming from solar, and after then wind and other non-renewable resources. You might know that we are third in solar, fourth in wind, and overall fourth in renewable energy resources. So what challenges does this renewable integration brings to the grid? We are shifting from thermal to solar and wind power. So what challenges? Grid concerns. As you know, solar are highly intermittent. They are dependent on sun capacity, sun shining, and winds are dependent on wind, how the wind is blowing, how fast it is blowing. So it makes grid operation very impossible. We are facing it. We are facing the bidirectional flow. We are seeing rapid ramp events. Let me tell you, compared to thermal and hydro, these renewable resources make ROCOF, rate of change of frequency, very high. And in electrical terms, you may be knowing that reactive power is the key to operate any machines. It gives the electrical and mechanical field to operate that machines. But if this reactive power increases too much, it makes the oscillations very high, and it relates to generation, generation failure, which ultimately led to grid failure. So some of the spatio-temporal dynamics. Why this opportunity has come up. In 2014, if you have asked me to talk about it, I would not have been done, because that time we were implementing WMS and PMUs through UR-TDSM project. What PMU does is give the actual data of the frequency and voltage on real-time basis. What SCADA does, it has a 10-second lag for these data. But what PMU does is give actual data. So we have the large amount of data with us. And in recent advent for AI technology, the technology is vast, it is growing. And data characteristics is 30 to 50 frames per second. So it gives an opportunity to find what if events, HILP events, much faster with our technologies in place. We will see in the next slide. My framework is based on two things, that is generative AI GANs, generative adversarial networks. The data is fed into DRL, deep reinforcement learning algorithms, which make this paradigm shift from reactive to proactive maintenance. And as you know, the transmission is planned through N-1 contingency, but it gives us a autonomous control over the grid systems. You can see there's pictures. Once PMU data is fed into gens, and then it is fed into DRL agents for coherency. It comes up to EHV grid, and it makes it a flexible assets. So my framework has three main pillars. That is WMS data foundation, wide area management system data foundation, which we have. We have implemented lots and lots of PMUs in our substation. We have digital substations. So we have large amount of data, real-time data, but we don't have any HILP event data because it has not occurred yet. It may occur, but it has not occurred yet, because we don't have any failure data, large event failure data. Then the second pillar is GN scenario synthesis. What GN does is it has two parts. One is generative, and other is deterministic. Generative part does the synthetic failures according to pin networks, and destructive check it for the actually happening in the real world scenario or not. So GAN scenario synthesis generates HILP event scenarios, what if scenarios, and it addresses the data scarcity, as I was talking about earlier, for rare grid events. It also learned from the historical PMU, weather and grid topology data that is fed into DRL. That's my framework, which when fed into DRL, it gives the agent to learn from optimal control. It also, the DRL agents learn from simulations, multiple millions of simulations, and it automatically adjusts the renewable devices such as FACTS and StatsCom to give the optimized amount of reactive power in the system. As you know, if there is a high injection of power but low demand, it makes high reactive power, which is ultimately translated to high oscillations and ultimately to generation failure, and ultimately after that to grid failure. So it maintains voltage stability and prevents oscillation propagation. Oscillation propagation, you may, if you are not electrical, you may think like that. When you create a wave, at the start, its impact is little bit low, but at the end, its impact is very high. That is oscillation effect. So the synergy, how can we make a synergy between GAN and augmented DRL? We can do three training approach. All AIs are trained on the data and then they are tested after that. So we can use the training approach, then the synthetic experience we have gained through GAN, then robust policy learning. After Git resilience, we can test it for the real-time online deployment. So you can see in this slide that I have talked about JANs plus DRL agents, which are giving grid control, and it is a proactive control. It gives the what-if scenarios, HILP scenarios, for the transmission outage grid failures, also known as black swan defense. And this framework is not just a hypothetication, it is, there are evidence from the existing research also. The F1 scores for the models have achieved near about 0.90 to 0.95, and F1 score of 1 is perfect. So you can see it is 90 to 95% perfect in predictive grid instability. Predictions can be made 4 seconds to minutes to hours in advance. And we have that DRL grid control also, which manages the fax devices more efficiently, and the frequency regulation is done. As you all must know that India is operating on 50 hertz frequency, and our frequency from 49.5 to 50.5 is acceptable. You know, in Spain, only 0.2 hertz drop in frequency beyond the limit caused the grid failure. So you must appreciate the fact that how difficult it is to manage the grid and push that voltage and electricity to your homes. The key insights have also research confirmed that DRL agents can execute complex real-time control actions for grid stability, outperforming traditional controllers across multiple metrics. You can see that graphs. If you compare the performance in conventional controllers, it is near about 4.5 seconds. In DRL agents, it is near about 3.6 seconds, which is 20% faster. In voltage control, the conventional controller takes about 150 milliseconds, and DRL agents takes about 100 milliseconds, which is 33% faster. The more it grows, the more it learns, it can go up to 50 milliseconds also. Then the oscillation dampening in conventional control is reactive, and in DRL agents, it is mostly predictive prediction. So DRL, the GAN data fed to DRL can teach DRL reach up to optimization for transmission networks. So what are the key conclusions? Key conclusion that from data reactive to we can go to generative proactive, and we can use the GAN synthesized data to be fed into DRL to use CNN networks and RNN networks, also the pin physics informed neural networks, to make a perfect transmission optimization. However, as all AI have limitation, it can't actually predict everything. But if we can predict 90 to 95% event, it will be very helpful in our case. So let's ponder and think, what is this actually? I must think everyone has seen the 2014 grid collapse in Eastern and Western region. Who have suffered it might be knowing it. We have not seen in recent years, in 11 years. But if the voltage drops very high, let's say sun is shining brightly in Gujarat and Rajasthan, and suddenly sun goes out, and it is a cloudy weather in Rajasthan and Gujarat, what will happen? All the solar panels will drop their voltages, oscillations will increase, and it will be a cascading effect to the grid, and ultimately the grid will collapse. So this glitch effects can be managed by the DRL by this way. The synthetic HILP generator checks for the historical limits. It generates its own data according to the pin philosophy. It also checks for the real-time events. It also generates its own data to match with the events, and then check historical PMU data, test against the historical PMU data. GANs are not only generate data, but it's also checked. So we can check the synthetic HILP events which can be happen in near future scenario, and it can be trained to predict all the further events. So this is just a photo to show you how grid can be helped under the umbrella of Jan and Shield DRL. So in the last, what is the suggestion for this strategic recommendation? We should invest more in data infrastructure. We have invested, but we should invest more. We are working towards accelerating digital twins. Digital twins are actually the system or computer twin of real-time transformers, circuit breakers. They they capture the real-time data, and if we have to do any simulation, we don't need to go to the transformer to do it. We can do it in the actual system and see what are the results. We should develop, and we are developing. PowerGrid is developing AI-ready grid, and we should invest more in data research as a government. Implementing these recommendations will accelerate India's decarbonization while enhancing grid resilience through AI innovation. Thank you. And if you are wondering what as I was saying in the beginning, it was, hello, how are you? Are you enjoying IEW and Goa? Hope you have a pleasant stay here. Today is a beautiful day. Thank you, Karthik. Thank you, IEW.
Thank you, Anand, for the enriching session and showcasing the complexity that our grid faces in the upcoming years, considering renewable sources are going to get integrated. So the management of the grid becomes even more very important. And by talking of the high impact, low probability event, detecting it earlier through AI and the architecture that was shown will be vital to ensure the stability of our grids in the near future. Thanks for putting that across beautifully and clearing up the Spanish translation for all the audience here. Now, moving on, our next speaker is Mr. Nishanth Raja. To set the context, we said while we spoke about the optimization of the grid, the key element fundamentally lies into where we are able to detect those elements. That means the sensors, which are crucial to detect those anomalies, report those changes, are something only when the actions can be taken or the models can be simulated. So here, we're talking of high temperature sensors, which are being a major challenge in the industry to detect it accurately and more reliably. So Mr. Nishanth holds more than 25 patents. Please correct me if I'm wrong subsequently, in this field of guided ultrasonic waves. And here, the truly innovated and incubated technology emerged from IIT Madras through his dedicated work there. And it's being spread across and winning awards as well. GAIL is one of the primary investors in this applications. And it's a matter of fact that this technology has been incubated in India. And without losing time, I would invite Dr. Nishanth Raja to come and brief us about his findings here.
Very good afternoon to everyone. Thanks for the great intro. I'm Nishanth Raja, co-founder and CEO of XYMA Analytics. I'm going to take you to a journey of showing how we are measuring some of the critical parameters that were unable to be measured with the current technology. And we identify some of the challenges which is harsh and hostile environments and unable to be accessed using the conventional sensor, and how we have innovated the technology to measure those technology measurements to the industrial. To make it very simple, we have the expertise in converting any metallic element or ceramic element into a sensor and help industries measure process parameters like temperature up to 1450 degrees Celsius using our patented sensor technology. I'll take you through the problem statement and then I'll jump onto the solution followed by the AI intelligence, which we are giving as a solution to the end users. If you see most of the operations that is happening in any of the refinery process, it can be a naphtha cracker, it can be a reformer tube, or it can be a DRA unit, VDU unit. Most of the skin temperature measurements are having failures because it still works on the principle of Seebeck effect, which dates back to 1960s or 70s. And most of the conventional sensors are of single point measurement. When a sensor fails, industry starts to lose from day one onwards. You need to put a manual intervention to do the corrective action. And real-time data, you have a pipeline, you have to maintain an optimum temperature to the pipeline, and when you overheat it beyond a particular design temperature, you'll start facing the creep damage into it, which prolongs over a period of time. So how to optimize this when we have a reliable solution where, without having some of the clearing some of the blind spots in the pipeline and having a uniform temperature homogeneity during this process. If you take the conventional sensors, either it can be thermocouple, pyrometer, or a thermal camera, the challenge with conventional temperatures like thermocouple, the major problem is with the junction failure over a period of time. And you need to either weld or brace this thermocouple to be attached to the element itself, where you have three different elements because you have two different elements in the thermocouple, and you have a third element which is the bracing, welding, or the attachment of the pipeline is the third element. So your coefficient of expansion is different for all three elements. So where the correction factor has to be included always. Next, coming to the thermal camera or the pyrometer into it. Both the optical based measurement require a line of sight, first of all, to do the measurements. And more importantly, it is going to give you the emissivity temperature, and always there's going to be a black body correction. For example, you put a black person or a white person in front of a thermal camera, the black body emission is much more captured than the white body emission. So when you go for a very high temperature application, the emission is not captured properly. So for which, what we introduce is world's first ultrasonic based waveguide sensor, where we can convert any metallic element or ceramic element into a sensor which can travel a length of close to 25 to 30 meters in a length. And what we are using is just an advancement of fiber optics. In fiber optics, you will be sending light rays, and using the wavelength change, they are measuring the surrounding medium parameters. In ultrasonic guided waves, what we are using is this can travel along the thickness of the wire over a length of 25 to 30 meters, and we keep periodic embodiments into this wire. It can be a bend, it can be a small notch, or it can be a small human-made intervention like a small hole into the section itself, where each point of intersection is going to be acting like a sensor for me. So wherever you want a measurement in a length of 20 meters, I'll make that embodiment, and using that embodiment, we can do the measurement. I'm just explaining the physics of how it is working. What you see over here in the rod shape is a metallic or a ceramic material. It is attached to an ultrasonic transducer. So you can see the ultrasonic waves traveling along the thickness of it, and due to impedance mismatch, you will get a reflection from it. Now I'm going to make an embodiment into it. It can be a small notch where you'll get another reflection from it. When temperature acts on this medium, two things happens. First, thermal expansion happens. Second, coefficient of, there is also change in the material properties, which leads to the wave velocity change. So by tracking that, we can predict what is the temperature acting on the surrounding medium. Like how you have the sound waves traveling in cold medium and hot medium, when you have an echo, there will be difference of sound waves which is traveling. The same physics has been included over here. And here, we can make multiple embodiments in a single wire, and we can do multi-point measurements at extreme temperatures up to 1450 degrees Celsius. And today, as we speak, XYMA sensors are installed close to 50 plus locations across the globe. It is completely indigenously developed in India, and we have close to 25 plus patents, both in India and in US together. And this is an example of one installation in one of the leading largest refinery in India, where they want to measure the skin temperature measurement of some of their pipelines and identify where exactly the coking is happening, so that they can identify the zone where the coking is happening, and they can pinpoint the heating parameters using the real-time data that is going to be coming from our sensors. So what we have told them was, starting from the optimization of it from day one onwards, how the thermal cycling has been happening, because you need to heat up from 0 to the particular temperature. You have a time frame for heating it. How the thermal cycling was looked into it at each zone, whether homogeneity of temperature has been maintained. We have introduced the physics-based AI intelligence into it, and using the one-dimensional temperature data from our sensors and the physics-induced model, we are able to predict the three-dimensional temperature profile of the asset to the end user. Today, as we speak, we are there in the Middle East, in the US market, Sweden, and also in some of the Indian installations too. And one of the major advantage compared to the conventional sensors, Either it can be a thermocouple or the optical based measurement like pyrometer, or it can be like a thermal camera. Whatever there was a challenge in the real-time hostile environment measurement, that has been already covered from using our sensor. Because more importantly, as a process engineers in many of the plant, they want the plant to be up and running and increase their throughput and efficiency. So they don't want a downtime into it. So asset optimization by making the thermal balancing into the asset is very important for them, which we are helping with the real-time data and providing them the optimization of the temperature using our patented sensor technology. Another example of our installations in some of the assets across the globe, and we are proud to say that is close to 10 plus years of research work which has gone into this technology, and close to 15 to 20 research scholars were worked on this technology, and it is purely made in India technology, and we won the National Technology Award from Government of India a couple of years back for this indigenously developed technology. It's going to be a disruptive technology to the industry, helping industry more efficiently, enhancing their throughput using our patented sensor technology. And this is another example where identifying the hotspots is very critical. Today, we are also doing the same sensor technologies implemented in aluminum industry, steel manufacturers, petrochemical industries, and also with the nuclear and other allied industries to it. And how we will identify the hotspots, because erosion of refractory happens over a period of time, and refractory erosion has to be monitored critically at different zones. So this is another example how we are able to identify the erosion of refractory, and over the thermal mapping of the complete asset using our sensor, we are able to predict the uniform temperature processing optimization using the patented XYMA sensors into it. Thank you.
It was wonderful hearing about the challenges of the different sensing elements. So, in this entire context of data acquisition, the challenges that what the conventional instruments pose in high temperature intensity zone was nicely clarified, and the technology that has come with continuous pursuance and relentless pursuit of excellence has led to development of this product, and the success story of installations in furnaces and crackers reflect the success of this. It's a matter of pride that it has been indigenously developed, and thanks a lot for sharing this, and hope your product is able to make a mark in the Indian market and globally as well. Thank you, Dr. Nishanth. Next, going in, as we saw entire innovation in the sensing element part. Now, once the sensors are there, we have the data that are coming in. So the data acquisition is taken care of. But this data acquisition, unless we are able to process huge amount of complex information to make sense of what an early prediction can help us avoid certain outages or plan better, will be vital for any continuous process industries. The next session will be presented by Mr. Nirmalganesh. He comes from MRPL and is a part of R&D team and the innovation cell there. The product that they have developed in-house based on continuous research, investing in high-performance computing, developing models for process or business critical application, which are traditionally single-line equipment, on the rotary machines has been phenomenal. And today, to help us understand how the early event detections or the anomalies has helped MRPL strive new heights is a really interesting case study. I invite Mr. Nirmal to please come in and share your experiences here.
Thank you. Thanks for the introduction. Good afternoon to everyone. It's an honor to be here. I am delighted to speak about Rotary Sentinel, which is an AI-based solution developed in-house by MRPL to improve the reliability of rotary equipment. We all keep hearing that AI transformation is happening at lightning speed. In fact, most of us are effectively using various AI tools to increase productivity in our day-to-day activities. But what is the situation when it comes to solving an industrial problem using AI? There have been various studies carried out by agencies like MIT, Gartner, and RAND, which suggest that more than 80% of AI projects fail, or they do not see any return on investments. More than 80%. So what could be the reason? Along with my presentation, I am also going to touch upon some of the key technical consideration which is going to minimize such failures. Getting into the topic, rotary missions are extremely important to ensure reliability of process units in any industry. These critical missions are generally standalone, and any sudden failure in this mission will have a cascading effect, and then it will have a huge impact on the business. The economic impact of not being reliable is also very high, which has been well studied by consultants like Solomon and McKinsey, which is well known to all of us. Let us see the existing practice in rotary equipment maintenance and certain limitations in that. Condition monitoring is generally carried out with the mission parameters such as vibration and temperature. There will be a condition monitoring software which takes all these inputs and then generates frequency plots, orbit plots, which then have to be analyzed by a vibration expert manually. The first thing to be noted here is that process parameters are not getting considered, because of which multi-dimensional analysis cannot be carried out. And there is no information about the operating efficiency of the mission. The next point is that manual intervention is required to interpret all the plots generated by the condition monitoring software, such as frequency plots, orbit plots. Again, you need expertise to analyze any root cause of any failures. Even to maintain the critical spares and handle inventory management, you need manual intervention. We heavily rely upon OEM-defined set points, which are static in nature, and we completely ignore the operating context. There have been various instances where missions have failed before even breaching these set points. So, considering the importance of rotary mission and the limitations whatever we have faced, and to overcome that, the solution what MRPL has developed is Rotary Sentinel, which is an agentic AI-based framework. It is an end-to-end automated system wherein multiple AI agents are running 24/7 in a collaborative mode. It can carry out analysis with respect to any issue of anomaly. It can also carry out root cause analysis. It can also give you prescriptive insights. It can monitor your mission efficiency. It can monitor your inventory. Over and above, it completely automates your condition monitoring analysis. Finally, there is also an interactive expert advisor to help our maintenance team. The key, this Rotary Sentinel is a one-stop solution for all the needs of rotary equipment maintenance. The key modules have been displayed here. First one being data and data integration. This is integrating data from different sources is the most challenging. This is where we have faced a lot of challenges, and then finally we were able to succeed. Wherever we did not have standard connectivity protocols, we have deployed software bots to fetch the data and send it to our AI models. So we were able to integrate the parameters such as mission parameters, process parameters, lab parameters, raw vibration signals directly from the condition monitoring system through API and various other connectivity protocols. So next, getting into the most important thing, AI with first principle is a crucial part of any architecture what we need to develop. Any output which is generated by AI needs to be validated with first principles or physics or thermodynamics or domain knowledge, whatever we can call it, without which AI models will definitely fail. We also have hybrid machine learning and deep learning based algorithms through which we have introduced a new concept called state degradation, and we are able to identify anomalies much in advance. When I say much in advance, it can go up to 8 months in some of the cases what we have actually realized. The next important concept is called causal analysis, which I will explain with a very simple example. You can see two charts shown here, each of them having two variables x and y. Can you identify in which chart y is related to x? So most of us would definitely accept that in both the charts y is related to x because it has got very high correlation. Let us see the results. The first chart is number of Disney movies released versus motor vehicle theft. The second chart is basketball league revenue versus fossil fuel use in Eritrea. Absolutely no relation between these parameters, but they have very, very high correlation. This is where causal analysis comes into play. to eliminate spurious correlation and then identify the exact root cause. By incorporating AI with first principles and causal analysis, our model accuracy improved, and then we were able to achieve an accuracy of 99.4% in one of the test cases. 99.4%. How good is it? Again, never believe such claims. Whoever says they have 99% accuracy. I will explain with another example. Let's say we have 10,000 people, out of which 10 are heart patients, and I am developing an AI model to detect people with heart issues. Even if I say all the people are healthy, my accuracy will be 99.9%, as you can see here. But do you see the issue here? Not even a single heart patient has been detected by our AI model, but still we have very high accuracy. So what is more important in this case is recall. As it was spoken by the previous speaker with respect to high impact incidents, this is where like such evaluation metrics comes into play. So recall is evaluation metrics which clearly says how many actual incidents are getting identified. Also, I can also say that all 10,000 are heart patients. Again, it is not going to be of any use to us. So that is where the next metric comes into play, called precision. Whenever we alert, is it real? Next one is early detection. As I previously mentioned, like we have introduced a concept of state degradation, because of which we are able to achieve, we are able to say bring out anomaly much in advance of close to 8 months. So this is the expert advisor, what I was referring earlier. This is where complete health report is available at one place of all the rotary missions. You can discuss about a specific mission, or you can discuss about all the missions. You can ask it to summarize the health of status of all the missions as well. You can ask it to generate trends. You can carry out different calculations using this expert advisor in an interactive mode. You can directly chat with this expert advisor and then get all the data. It also does all the anomaly analysis. It gives us root cause analysis. It monitors your inventory. It also generates all the alerts on real time. The important thing to note here is that all these models are running locally. Data privacy has been completely ensured here. Again, as I was mentioning earlier, condition monitoring activity has been now automated. Spectrum analysis, orbit analysis, everything is carried out by this expert advisor, including generation of the report and interpretation of the results. Root cause analysis with very clear recommendation whether to go for a shutdown or whether to continue to run the mission. Everything is clearly available in this expert advisor. All these outputs are also directly sent to a dashboard with real-time alerts. These models are continuously being trained and fine-tuned with domain knowledge using our in-house domain experts. This is an overview dashboard where we get all critical information for our stakeholders. It has got various drill-down pages. It exactly pinpoints whether compressor has an issue or turbine has an issue. You can also go to tag level monitoring. It exactly tells you which tag has got a problem in your anomaly. You can monitor the efficiency. You can monitor the inventory. You can configure all your inventory levels and then leave it. It is automatically going to take care of your inventory as well. Whenever an anomaly is detected, it is automatically going to identify what are the spares required. Is my spare available in my inventory? If not, whether should I take any action? Everything has been automated. Excuse me, slide is not moving. Yeah. Coming to the benefits, because of Rotary Sentinel, we have got early warnings in 4 critical missions, as I said earlier, which is close to 6 months to 8 months in advance. So it has helped us to plan very well and then reduce the number of shutdown days, because we have eliminated the surprise element. We clearly know what exactly has to be attended in the mission once we take it for maintenance. It has also helped us to maintain all the spare availability before maintenance, because we are getting early warning. We are able to automate the condition monitoring system. Comprehensive root cause analysis also is available there, which has increased the efficiency of our team. This is acting like an end-to-end assistance for our maintenance team. To summarize, we are able to move from reactive to predictive and prescriptive mode, because the expert advisor itself is able to tell us what has to be carried out to avoid the failure. So just to summarize whatever key technical things we have discussed, this is not an exhaustive list. There are various other non-technical things like cultural change, upskilling, etc., which are also equally important. These are the technical aspects which are generally not discussed by anyone. Rotary Sentinel is just one application what MRPL has developed. We have various other applications focusing on process optimization, energy efficiency, reliability of asserts. We are the first refinery to win 4 back-to-back innovation awards from Government of India. And learning what we have achieved with all these experiences that it is easier for a domain expertise to learn AI rather than making a AI developer to learn our domain. So for the benefit of everyone, I have compiled certain links in this QR code. You can share, you can scan and then get all the open source courses from Stanford and MIT, which is going to be of very use to you. So finally, I would like to conclude with an old saying: 3 things cannot be hidden for long: the sun, the moon, and the truth. With MRPL's Rotary Sentinel, the truth about mission can no longer remain hidden. Thank you. Thanks for your time and attention. Thank you.
I think the session was pretty engaging, but till the true success will come when you actually know why a machine fails on a Sunday, holiday, or a night shift when people aren't there, right? So being in the maintenance background where I started my career, that was something which always bothered. But now that we're able to predict and prevent a catastrophic event, and the showcase of how 4 critical machineries were detected earlier with almost 99.4% accuracy, plus events which were detected as early as 8 months in advance. That's a boon to any process industries which has to take in extensive planning exercises and efforts to predict and plan the downstream activities. Thanks for presenting your cases over here and enlightening about the innovation awards that has been won. Next upon, as we saw in the first session, we're talking about renewables integration as well. So we are talking the power of AI in which areas that can go in. So as renewables is a complex topic and most sought out in the today's environment of accelerated decarbonization goals which are expected to be met. We have with us Dr. Abhineet, who comes with a lot of background around computational fluid dynamics, being an aerospace engineer by qualification as well. As a part of this discussion today, and his role in Shell, where he focuses predominantly on renewable sources like hydrogen, wind farm, and so on. Here's an attempt to showcase how, as end users, we could maximize the power intensity based on our investments that are coming on for power generations as such. So without wasting much time, let me invite Dr. Abhineet to share his thoughts on this topic.
A very good afternoon. I'm Abhineet Gupta. I will talk about physics-informed neural networks for modeling energy systems. I will focus on a work that we did with Indian Institute of Science to model wind farms using the physics-informed neural networks. And I will slightly go deep dive into what physics-informed neural networks are and why they could be used or can form a basis of future digital twin type applications. I will also touch on 2 additional applications around the reservoir flow modeling and another one around the drilling. So with that, let's get started. This is just a cautionary note. So why do we need physics-informed machine learning, or why do we need machine learning to begin with? The idea is to model and predict the variables of interest in the domain that we work in. But the challenge is, for most of the applications, the accuracy or the fidelity of the models also results in an increase in the time that it needs to run those models or the application. The work or the idea for this work is to bridge that gap and have models which are as accurate as the highest fidelity models available there, while almost instantaneous, allowing a real-time inference and real-time decision-making. Now, what type of models can we look at? There is, of course, a spectrum. On the extreme right side, you see the traditional ML machine learning models. Those machine learning models typically rely on a large amount of data set, labeled data set, which is usually sparse in the energy industry. What we have in the energy industry is understanding of the governing equations, governing physics of the system, and some sparse data. Now, that's where pins combined with some data in applications like physics-informed neural operators comes into picture, and together form a kind of a powerful combination which can help bridge this gap between accuracy and computational time needed for modeling some of the energy systems. Now, I'll just do a 1-minute crash course on pins. So what pins exactly are? If you have some exposure to the computational fluid dynamics, they are very much similar. The major difference is it's kind of a mesh-free method, so we don't rely on a grid. And instead of using a discretization to compute the variables of interest, here in the pins, we use a neural network to compute the variables of interest. As an example, if we want to simulate the flow in a wind tunnel, what we need is the domain, that is the tunnel. We need the boundary, that is the vehicle surface. We need the variables of interest, that is the velocities and the pressure. What we essentially do in pins or physics-informed neural networks is pass those input through a neural network, initialize with some weights, and we get the output, which are the velocities and the pressure. Now, we can use a technique called autograd to compute the derivatives and use those derivatives to compute the governing equations of the system. In this case, the governing equation will be the Navier-Stokes equation or the incompressible flow equation. Now, once we have the governing flow equation, we can try to optimize the weights of the networks or the parameters of the neural networks to ensure that our residual, the partial differential or the governing equation based residual goes to 0. So essentially, instead of using data to drive the losses to 0, here we are using the known understanding of the derivatives of the system to drive the losses in the domain to 0. Now, of course, that's easier said than done, and that's one of the major limitations that I see currently in use of pins, because every problem, every application is different, and essentially it requires us to really look into the optimization and the weightage strategy, the convergence strategies to make that particular problem work. In this case that I'll present of the wind farm modeling, the governing equations are the flow equations, the mass conservation equations, and the turbulence closure equations, which are written here by the K and the epsilon. Now, what we need to do is to ensure that and we are not solving just a single set of equations. Essentially, it's solving a system of partial differential equations, which means we cannot let one equation determine the losses or govern the output of the system. And that's where a weighting strategy comes into picture. So those iterations goes into making such system works along with coming up with the good convergence strategies. But once we know how to make such a neural network converge for a given set of system or given set of equation, this is how the results looks like. So here on the left, you see the representation of a single wind turbine taken from a slice, looking at the slice from the top. And at the bottom, you see the velocity field, again, looking at the velocity contours from the top, turbulence intensity contours, and the pressure contours. The wake signature is obvious here, that we see that the velocity deficit behind a wind turbine and increase in the turbulence intensity, decrease in the pressure behind the wind turbine. But we also did a quantitative analysis which is shown in the plots on the top right corner, where we at multiple distances downstream of the wind turbine for a pilot wind turbine, where there's of course abundance of data available to compare against. We compare the physics-informed neural network-based output to the CFD outputs for multiple turbulence closure models, and also with the data that is available from that particular site. The results were convincing, and the work has been published in the Physics of Fluid journal last year. Now, just solving one wind turbine is not enough. If you want to really optimize a wind farm from the perspective of optimizing the operations, and also from the perspective of quickly iterating among different designs to be able to come up with the optimal design for a wind farm, we need to simulate multiple wind turbines. Now, when we go from a single wind turbine to a multiple wind turbine, we realize that solely relying on the physics-based input is not enough for the neural network to converge. And that's where the use of hybrid modeling, where we use sparse data available along with the understanding the physics of the systems, comes into picture. So here we use a hybrid training strategy where we use the PDE loss, as I mentioned in one of the earlier slides, but supplemented it with the SCADA measurements at a given plane. Only the velocity measurements not in the entire domain, but in a given plane in the domain. And with that, using the pins, we were able to recover or predict the flow field in the entire domain, and not just the u velocity, which was given as an input, but the entire flow field as in the different velocity components and the pressure. This basically, for an operator, gives an insight that it helps him to recreate the entire flow in the domain, which gives insight to the multi-variables, multi-height data set, which eventually helps the operator to optimize it from the perspective of your control, as well as derating the wind turbine. Now, and this essentially, such engines can sit at the core of a digital twin, which can help eventually to reduce the design time to get the optimum design by quickly iterating over multiple designs, as well as for the real-time optimization techniques. In this case, for example, for the wind farm, it could be the yaw control or moving the wind turbine to adjust the flow in the domain. Now, this is just one example that I have touched. We are currently working on multiple such examples where similar framework using some physics and some data set is being used to model different applications across energy industry. One of them is in the LNG domain, where we are using such methods to model the heat exchangers. Another one is in the hydrocracker domain and the downstream. Then there's another one that is in the reservoir flow modeling, and then for the drilling work. So the last two I'll quickly touch upon. We are working currently with multiple universities across the globe to predict the reservoir flow using physics-informed neural networks over in a multi-agentic framework, where the idea is again very similar, that we have the data set available for multiple reservoirs. On top of that, we couple the black oil equation-based loss functions in the overall network architecture to predict the flow physics or the reservoir flow better. There are such simulators available which predicts the different subsurface flow conditions. What such methodology helps is quickly iterate over multiple designs, quickly iterate over multiple geological complexities, and essentially giving a diverse outcome, which helps in the uncertainty quantification and accordingly help the business leader take a call on the risks involved in the particular development. Another such application that we are currently exploring is used for the wells simulation, where we want to understand the rate of penetration for the wells, as well as would like to look into the multiple drilling dysfunctions. Now, this is a problem slightly different in the sense that the physics alone cannot solve or is not as well understood, so that we can capture really or predict the dysfunctions a priori, as well as the data set is also spare. So here is another area where both physics and data can come together to give better predictions into what should be the rate of penetration for the given well, given we understand some of the physics and we have the long time history of the data sets for that particular well. So with that, I will come to the conclusion. What I would like to have you as a takeaway from this work is that for the development of future digital twins, for optimizing operations in energy industry, as well as for having better design of different assets, it's physics plus data-driven models can really be the game changer. Second thing is, though such physics-informed neural network models take more time when we train them compared to the conventional solvers, once they are trained, they can be much faster, allowing real-time inference, which helps essentially in the improving the asset performance, and basically having faster design and at the much lower expense. With that, I would like to acknowledge many colleagues from Shell and ISC who help in this work, and happy to discuss if you have any questions later.
I think we had a high voltage session now. Thanks for simplifying the neural network concepts over here. But as we see, the concepts that can bring and optimize our investments, just as the example that was shown on the wind turbine layouts, considering the geographies of the licensing for a given area, we would have different variations, elevations, and the wind velocities that would be absorbed. But the maximization would come from how much power we can extract from these sources as such. The models like this, it's possible that we can maximize it by having the accurate layouts. And I think that will be a very prominent discussion point, which probably we can catch up with our speaker post this call. Thanks a lot, Dr. Abhineet, for sharing your insights on this. Now, as we come in, our next speaker is Mr. Ravi. He comes from BP. He's a kind of an enterprise architect, has been working with IT giants across. And today, while we saw the examples from our data acquisitions, there is an element of data storage. Now, most of these models require high compute strength. That makes it really important that how we can leverage, and it should not be a deterrent for us to make our AI investments or investments in any sort to build those models and so. At this juncture where a lot of clients are working across to streamline their investment, here is a thought where Ravi would want to share his ideas about how the compute investments can be brought into life by a different approach as such. And happy to invite Mr. Ravi to come and share his thoughts.
Thanks a lot, Karthik, for setting the context. Makes my presentation a little more easier. So yeah, the topic is the hidden supercomputer. And when we talk about compute, traditionally what we have seen in past decade is we've been trying to scale up, and that probably, when I was trying to understand how the compute world has evolved across the past few decades, I started asking a fundamental question that comes from the very humble backgrounds that I come from. So in an Indian family, whenever our toothpaste used to get finished, or was about to get finished, we would ask our parents to probably procure a new one. But the answer was, we can squeeze it and then use it for another few days. And then on the same thought process, I started to explore a little on how the compute works in an enterprise context and how we could optimize things in general. And just to make sure it doesn't become too overwhelming or not taking too much of a technical deep dive, I'll start with the very basics, which is what compute is. So if we look at compute, it's nothing but a digital horsepower. So in a car, the more horsepower you have, basically the more you could get out of it, whether it's speed, whether it's the output that you're looking for. And if you further break it down, compute generally is just a CPU, which probably you could hold in your palm, as you see in that picture. And the unit at which compute works is a flop. So just to break it down, if I did a 2 plus 3 on a calculator, that's one flop. And today, the flops per CPUs are increasing. But at the same time, can I get the best out of it is what we'll try to explore here. So moving on, where is compute? I think it's everywhere. All of us have phones. There is compute present there. We have quite a few laptops here. There's compute. And if we take it to the enterprise context, I think it's the data centers. So data centers are in a way the compute factories. And that's where the compute lies in the enterprise context. And we are all in one or the other way consumers of these compute via data centers. So further down, I think the data center race in a way has begun. You go back in 2019, we had roughly 600 plus or somewhere in that range, 600 data centers across the world. In past 5 or 6 years, that has grown more than 2 times. So as of today, 2025, we roughly have 1,300 data centers running across the globe. And we spoke about flops. So it's roughly 300 to 500 exaflop of compute that is being generated out of these 1,300 data centers. And one of the other biggest consumers is, at least in the energy sector, is the HPC compute. So if you look at it, that's again 13.8 exaflops being generated there. 2030 prediction says it'll grow by 3 times from what it is today. So we are looking at probably over 4,000 to 5,000 data centers by 2030. So the question is, what is the price that we pay? And this is approx figures per 100 megawatt data center. So essentially, the price you'll end up paying for it or basically building it will be a few $billion for sure. But I would want to talk about the price we pay in terms of our environment. CO2 emissions per year, roughly 350,000 tons, 800 gigawatt of energy being consumed per data center, 730 millions of water being consumed, and one data center roughly takes around 40 acres of land as well. Now, moving on. What's the global footprint as of today? We are looking at 50,000 acres of land, 450 terawatt worth of energy, 450 metric tons of CO2 emissions, and roughly 560 billion liters of water being consumed. And this is the number from 2025 gathered out of different resources available publicly. Now the projections are, with this growing 3 times, we are looking at maybe somewhere in the range of 900 plus terawatts worth of energy being consumed. The water usage looks like 1.2 billion liters per year. CO2 emissions, 270 to 300 metric tons per year. Land usage, probably 100,000 plus acres of land. So for the price we are paying, and we want to grow as a race or we want to evolve, and this is a necessity. But coming back to the question, are we utilizing our existing resources to the max capacity? And that's what we'll try to figure out here. So as we said, it's flops, right? That's what makes the compute and eventually a supercomputer. So if we spoke just in the IEW context, we have roughly 75,000 people attending this conference, which is at least a 75,000 plus phones, which has compute. I'm sure there are a few thousand laptops as well. I'm sure nobody or most of us probably are not using our phones at this point of time. Yeah. So most of it stays idle, whether it's enterprise laptop or phones, a lot of times, probably 50% times, 50% of the entire day. Now, what if all these phones just work together to cater to a specific workload? It's possible, because in the end, to run something, all you need is a CPU, yeah? So essentially, we don't lack the compute, but we lack orchestration. And if I could just give you the numbers, just with IEW, the amount of compute we can generate is almost equivalent to half of one of the world's finest supercomputers. And almost 1/6 of an exascale AI data center is the compute that's just available within IEW 2026. But it's all noise until or unless you orchestrate it or bring everything together. And we'll go how we do it. So there's just all the phones working in silos, fair enough. But what if there was an orchestrator in between, which is just a software which can ensure that any workload that comes in securely, safely, can use the existing devices, perform the compute, send back the result to the orchestrator, and that's possible. Now, in an enterprise context, we at least would have, any enterprise, I'm looking at maybe 50,000 employees, 50,000 to 100,000 employees. Each employee has a laptop with a very decent amount, probably at least 8 vCores and 16 GB to 32 GB worth of RAM. So that's something that all the enterprises have already paid for. How much are we utilizing it to its fullest capacity? Probably not. Maybe a 20 to 30% is what we ideally use in the entire day. So if the same orchestrator could connect just to the enterprise laptops and some of the non-critical workloads could be pushed down to these existing laptops, for an enterprise like BP, we are looking at least a few $1 million worth of cost savings in compute area. And today the need of the hour to scale up the compute is we want to explore AI a lot, and that takes a lot of compute. So a lot of exploration work can be pushed to these distributed compute setup. Sustainability, we spoke about the number about the data centers and the kind of impact they have on our environment. And you've already paid for it, so there's no capex involved at all. Now, that was the enterprise context. I would move on to the India vision. And this is the data published by our own ministry. And this is probably the 2024 report, where we have roughly 800 million smartphones, 800 million plus, and I'm sure the number has grown drastically in last couple of years. We have 60 plus million laptops and PCs lying idle almost 70 to 80% of the time. And we might be sitting on the world's largest latent compute network as a country. Even if each one of these devices, not even each one, I'm looking at maybe 1 to 2% of what we have lying idle today. Out of that, if we could just extract 150 G flops, which is again probably 10% max of what we have, we can build our own sovereign indigenous data center, a virtual data center, and that's possible. The sectors it can help, anywhere where compute is needed. I've tried to list down a few, which is energy, climate, healthcare, education, and AI, and startup research. So, but wherever you need compute, I think the same orchestrator could help you, repurpose the existing compute. Now, when I started the research on it, it did feel like maybe this is ahead of its time. But then the research turned out that the tech exists since past 25 years. So the first kind of this implementation was done in late 90s, where a project called SETI at Home, which was mainly focused towards a volunteer distributed compute network or a mesh, where radio signal related workload was being distributed across volunteer systems. And a lot of research was carried out using a very similar setup. Moving on, folding at home, which is in the healthcare sector. I think this is mainly around research for proteins, which is a very, very compute heavy domain. So folding at home as a project on the same concept has been running since 2000, and it's still ongoing. In 2022, the Berkeley University came up with something called Boeing Framework, which is an open source framework, which kind of makes it the same architecture publicly available. So it's all about just repurposing that and then using it in our own use cases. And the implementation of Boeing Framework, you'll see at HEP at Home, which is CERN, the Hadron Collider, or the research, one of the finest research facilities across the world. CERN uses it. Minecraft at Home is using it, again, in a lot of areas. So the tech exists. The only thing we probably need to do is gather the pieces of puzzle, put it together, and figure out how we could use it in our domains or day-to-day lives. And what's probably required is not a lot of capital. It's just us coming together as an enterprise, we should start exploring such tech, or we should start investing a little in making this possible. As policymakers, since this is India Energy Week, and I am hopeful we have a lot of policymakers here in the room or across, we need to focus on a public mesh which can incentivize. So imagine me being able to volunteer my phone and getting some incentive out of it. If we incentivize it, I said maybe one exascale data center, but we might be able to build probably 10 of those within a year is possible if we had the right support from the government. And as my fellow researchers, the need of the hour is, and I could see a lot of us researching in similar areas. So the need of the hour is probably to advance this research in a direction where this sees an implementation in the energy sector as well. And with that, I think I'm at the end of the time. And my request is to just start a conversation, start a dialogue, start discussing how we could optimize what already exists rather than looking at just scaling up. With that, I will end my presentation. Thanks a lot for hearing and for your patience.
So as we heard, Ravi, the power of distributed computations, probably it has triggered a thought in us that how we can think about it and contribute or do our bit in the coming future as well. Thanks a lot for simplifying the concept of the hidden supercomputer. I know right now we stand between the lunch and the close of the session. So, but I'll be failing in my part if I fail to thank the organizers and the India Energy Week giving us an opportunity to present us and hear us. Thanks a lot, all the patient audience and the panelists, for sticking to your time and sharing your insights. I'm sure the insights that and the takeaways that we carry from the sensing technologies that's going to pioneer in the near future, the power of AI, the optimization that we are talking in terms of the transmission network stabilization, the intensive neural networks that we intend to put to optimize the capital investments are going to shape the way we do it. Also, right now, as we are closing this thought on the power of distributed computing, hope these things trigger a thought and add value to our conversations. I, Karthik Rai Kadenja, part of EY Parthenon, thanks all of you for your attentive hearing and have a great lunch ahead. Thank you.